We've been talking about Boolean formulas and Boolean expressions. I wanted to go over some notation and talk about equivalences between formulas or expressions. So let's say that we have a Boolean formula f, and it involves the literals x1, x2, and x3. How many different assignments are there to the literals x1, x2, and x3? It's fairly easy to see that there are 8 assignments. For example, true, 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 false, true, false, false, and so on and so forth, all the way down to false, false, false. Okay, so for any Boolean formula on 3 literals, there are 8 possible assignments we could give to the literals. And I'm going to write, this is a curly brace, true, comma, false, curly brace, raised to the power 3. This denotes the set of all possible assignments of length 3. Okay, so this is the set of all assignments that you could give to 3 literals. Each value takes on true or false, and it's of length 3. If I wanted all assignments of length 4, all true, false assignments of length 4, I'd write TF to the 4th, and so on and so forth. Okay, so what does it mean for a formula to be satisfiable? How do we write that using some notation? Well, we would say f is satisfiable if there exists a z that lives in this set, true, false to the 3. I'm writing a 3 here because f here has 3 literals. So if there exists a z that is an assignment of length 3 such that f on z evaluates to true or simplifies to true. And what does it mean for a formula to be unsatisfiable? Well, f is not satisfiable if, and here I'm going to use an upside down a. This is, you read this as for every, it's shorthand for every. If for every z in true, false, the 3, f of z simplifies to false. Okay, so f is satisfiable if there exists an assignment that makes it true, and it's not satisfiable if for every assignment z in true, false, for every assignment of length 3, f of z is equivalent to false. Okay. So let's say that I have 2 Boolean formulas, f of x1 up to x7, let's say, and then I have g of x1 up to x7. We're going to write that f is equivalent to g, and I'll use 3 bars here. So f is equivalent to g if for every assignment, for every truth assignment of length 7, f of z takes the same value of g of z. So if for every assignment of true, false of length 7 that you put inside f, whatever value you get, you should get the identical value when you plug it into g. And this is how we proved one of the distributive law for Boolean formulas a module ago. Here are some other equivalences that are important and you may encounter. So the first one is De Morgan's law. And this states that the negation of P and Q, where P and Q are formulas, is equivalent to not P or not Q. Okay, so for example, not x1 and x2 is equivalent to the formula not x1 or not x2. And also there's part 2 of De Morgan's law, that is that not P or Q where again P or Q are formulas, is equivalent to not P and not Q. Again, P and Q are formulas. So also, for example, if we had not x1 or x2, this is equivalent to not x1 and not x2. Here are some other equivalences that might be useful for you. One is the double negation law. So if I have a Boolean formula P and I look at its negation, and then I take the negation of that, this is equivalent to P. Also, if I look at P or not P, where P is a Boolean formula or expression, this is equivalent to true, the constant true. And if I look at P and not P, this is equivalent to the constant false. In the Rosen book, you'll find some other equivalences that are quite simple, and I'm not going to spend time on, but you might want to review them just to help you simplify Boolean formulas in the future. A special type of Boolean formula that I want to talk about are DNF formulas. Now the DNF stands for disjunctive normal form. It's not important that you know what it is. What is important is that you understand the structure of a DNF formula. So what is a DNF formula? Well, it's anything that's written as an OR of ANDs. Okay? So if we have x1 and x2 and x3, or x4 and x5 and x6. This is a DNF formula because it's an OR of two ANDs. Now we could have x1 and x2, or x2 bar, or x3 and x1. This is also a DNF formula. It's the OR of three ANDs. Here's an AND, here's an AND. I mean, just a literal of size 1 is an AND of size 1. And here's another AND. Okay? So sometimes when I'm writing DNF formulas, I'll omit this little AND here, the caret. So I might write F as x1, x2, or x2 bar, or x3, x6. Okay, so I'm just writing it without the parentheses, and I'm omitting this little AND here. But the AND should be clear from context. Just like sometimes when you leave out an X or a dot in an arithmetic expression, you mean multiplication. Okay, so a DNF formula is always an OR of ANDs. And then there's something called CNF formulas. And instead of being OR of ANDs, these are ANDs of ORs. So for example, if I write F equals x1 or x2 or x3 and x4 or x5, well, it's an AND of two ORs. So it's a CNF formula. I could also write F to be x1 or x7 and x2 bar and x3 or x1 bar. Now again, this x2 bar can be thought of as an OR because any literal is sort of an OR of size 1. It's also an AND of size 1. But here we have the ANDs of three ORs. Here's the first OR, here's the second OR, and here's the third OR. Okay, this is a CNF formula. It turns out that any formula on literals that you can write can be transformed and written as either a DNF formula or a CNF formula. I guess I never said that the CNF stands for conjunctive normal form. And these are two commonly studied types of Boolean formulas that we'll come back to and sort of explore in the future.